Resist, resource-efficient satellite image segmentation tool. Let's start with an introduction about the project. As you know, Mars is the fourth planet in our solar system. Over the years, Mars has been photographed by satellites numerous times, and the images have been sent back to Earth. Satellite images of certain areas on Mars show the existence of extensive systems of meandering ridges, formed due to deposition of material over the years. As you can see in this diagram, these ridges are continuous positive channels that form a sinuous pattern and are called inverted channels, inverted in the sense that they actually rise above the ground. Now, the presence of these inverted channels is one of the most convincing evidences of past fluvial activity on Mars, so geologists are interested in mapping the distribution of these channels. What our project aims to do is to develop a tool which can automatically segment these inverted channels in a resource-efficient manner, while preserving a high accuracy. So, let's take a look at the problem at hand. The first problem is that currently there are no models that segment inverted channels from high-res images. Also, there's no annotated dataset of inverted channels for us to train a model on. And the final problem is that since high-res images are of very high resolution, segmenting inverted channels from them requires a lot of computational resources. Let's explore the project objectives and their significance. Inverted channels in high-res images span a vast area. It is crucial to capture contextual information when segmenting them. Thus, the first objective was to implement a context-enhanced segmentation approach capable of capturing contextual details across different scales. The next objective was to design a post-processing layer that could minimize possible erroneous predictions resulting from the ambiguities present in Martian terrain. Third objective was to implement the final segmentation tool in a resource-efficient manner, enabling it to process high-resolution images with limited memory and computational power. At the project's commencement, we lacked an existing labeled dataset. Without a dataset, any model development work would have been impossible. Hence, an objective was set to create one. The initial dataset we prepared consists of 23 high-res images of Mars. These images not only include the inverted channels, but also encompass ambiguous features such as crater rims and wrinkle edges that can be mistakenly identified as inverted channels. Each image has a fixed width, while their height varies. The file size of each image can range from 2 megabytes to 10 megabytes. As a result, the total size of the dataset amounts to 120 megabytes. The methodology starts by dividing the initial dataset into training and testing sets. To handle memory constraints, both sets are further divided into patches of two different sizes, 256 by 256 pixels and 512 by 512 pixels. The class imbalance between background and inverted channel pixels is addressed by separating the patches based on a 5% threshold of inverted channel pixels. For the smaller 256 by 256 pixel patches, data augmentation techniques are applied to balance the classes. The patches belonging to the inverted channel class undergo random rotation and additive Gaussian noise. Meanwhile, random undersampling is applied to the background class patches. In the case of larger 512 by 512 pixel patches, the dataset can be balanced solely by augmenting the patches of the inverted channel class. This methodology results in two distinct datasets for training and testing segmentation models, one comprising small image patches and the other comprising large image patches. Using the 256 by 256 dataset, we train a context-deprived model, and using the 512 by 512 dataset, we train a context-extended model, and later we combine them into the context-enhanced model. Now let's look at how we implement the context-deprived model. For the context-deprived ensemble model, we trained a UNet model and an ITERNet model using a customized loss function named weighted focal dice loss function. The final segmentation output was produced by taking the union of the outputs of the two models and stitching the patches together. Now let us look into a sample animated segmentation of the context-deprived model. The context-deprived model captures fine details of the image patches, but has limited contextual information on the overall satellite image. As a result, the model will have a higher true positive rate, but also a relatively higher false positive rate. Small features like ridges, impact craters, and small valleys have also been identified as inverted channels in this context-deprived model. Now it is time to look into how we implemented the context-extended model. For the context-extended ensemble model, we trained UNet, SA-UNet, and Attention UNet models using a customized loss function named Weighted Focal Dice Cross-Entropy Loss Function. The final segmentation output was produced by taking the probability voting of the outputs of the three models and stitching the patches together. Now let us look at a sample animated output of a context-extended model for the same satellite image. The context-extended model has higher contextual information on the overall image, enabling it to distinguish between small features like ridges, impact craters, and small valleys, as well as relatively large features like inverted channels. However, the model may not capture the complete structure of inverted channels as they ignore fine details. Nonetheless, the models will still be able to capture the outline of inverted channels, resulting in a relatively low false positive rate. Now, the two models have complementary strengths and weaknesses, and by combining these two approaches, we can extract the strengths of each model and produce more accurate results. To do this, we select a 64 by 64 kernel from the context-deprived segmentation model output and verify its segmentation with a 192 by 192 kernel from the context-extended model output. We do this process iteratively for the whole image, and it allows us to extract both the fine details captured by the context-deprived model and the larger-scale features captured by the context-extended model. Now, as you can see, this output still has false positives and gaps. To minimize these and produce a more accurate output, we implemented a post-processing layer. Our post-processing layer consists of three main parts: the extended bounding box overlap layer, the gap-filling layer, and the interior region filling layer. Let's first look at how the extended bounding box overlap approach works. This is done to minimize the number of false positives in the segmentation output by leveraging the curvilinear and continuous structure of inverted channels. We start by identifying the individual contours in our segmentation output, and we draw bounding boxes around them. Next, we extend those bounding boxes according to their size and identify and select the longest contour. We then select the bounding boxes that overlap with the selected longest bounding box. We do this process iteratively until no other overlapping bounding boxes are found, and remove the rest of the contours. However, there were still discontinuities in the output. To minimize these discontinuities, we introduced the gap-filling layer. Here, first we skeletonized the segmentation output. This basically thinned down the inverted channel predictions into skeletal segments that are 1 pixel in width. Next, we identified the coordinates of the end pixels of the skeletal segments and joined the discrete skeletal pieces which are in the close range. These newly introduced gap fills were then dilated to create a segmentation output that only consisted of the gaps to be filled. Finally, the union of the earlier segmentation output and the gap fills was taken to produce an output with less discontinuities. The final interior region filling layer was implemented to remove interior regions of false negatives in the segmentation output. Here, we applied morphological operations to fill in interior pixels of connected components in the gap-filled skeleton. The final output was taken as the union of earlier created gap-filled segmentation output and the interior region-filled skeleton. So now, let us look at the final results. The left column of this image has the high-rise images, the middle column has the ground truths, and the right column has the segmentations generated by our pipeline. This graph nicely summarizes the progress of evaluation scores with the models we used. The basic models had high F1 scores and Jacquard scores, but the AUC score was around 0.5. Even with pre-processing, the AUC score increased only up to 0.6. Next, in the context-deprived model, we increased the AUC score, but the F1 and Jacquard scores were reduced. On the other hand, in the context-extended model, we got high F1 and Jacquard scores, but a low AUC score. By combining the two models in the context-enhanced model, we were able to gain sufficient scores for all three evaluation criteria. After applying the post-processing layers, we were able to score an F1 score of 0.96, Jacquard score of 0.94, and an AUC score of 0.84. Finally, let's see a short demonstration on how Resist web application can be used to segment inverted channels on Mars satellite images.
Hi there. Welcome to Resist, the resource-efficient satellite image segmentation tool. Are you tired of manually segmenting satellite images? Well, say no more. With Resist, you can now effortlessly segment high-res satellite images for inverted channels and generate efficient, accurate, and precise results. It's time to revolutionize the way you work with satellite imagery. Now, let's dive right into the exciting features of Resist. To start annotating high-res images automatically, simply click on Get Started. Upon clicking Get Started, you will be redirected to a new page where you have two convenient options. Option 1. If you already have a specific high-res image in mind that you want to segment, you can simply enter its ID in the provided field. Once you've entered the image ID, click Search and Resist will fetch the image for you. Upon clicking on the image, you will be able to see the high-res image along with its name, ID, longitude and latitude. Click on Generate Mask and Resist will automatically start processing the image and generate the segmented results. Behind the scenes, Resist leverages advanced algorithms and cutting-edge techniques to automatically segment the high-res images for the inverted channels. While the processing takes place, you can sit back and relax, knowing that Resist is working diligently to generate the most precise results for you. After a short wait, Resist will present you with the segmented satellite image showcasing the inverted channels with efficiency, accuracy, and precision. After a mask is generated, it will be displayed as a layer on top of the high-res image. You have the option to hide or unhide the mask. Additionally, you can download the high-res image and the mask separately using these provided buttons. Option 2. If you want to search for high-res images in a specific area and segment them individually, Resist has got you covered as well. For this, navigate to the Large-Scale Exploration section. Specify the area you want to search for inverted channels using coordinates and click Search. Resist will search and retrieve all available high-res images within that region. Once the search is complete, you will have a list of high-res images to choose from. Simply select an image you wish to segment and generate the mask. Now, by using Resist, you can spend less time on manual segmentation and more time focusing on the analysis and the insights provided by these incredible satellite images. Thank you for joining us with this demonstration. Experience the power of Resist today and unlock the full potential of satellite imagery.